Hello everyone, we are going to solve this given oblique triangle. We are to choose between the use of law of sines or law of cosines, but please be guided that before we could determine which is which, we can refer all of them on the given measurements. Here, we are given with one angle measurement and two side measurements. These forms of measurements do not fall on SAS category since we have our given angle is not included between two sides because we are given with a pair of an angle in its opposite side. In this scenario, this is an example of an SSA situation. For SSA situation, we shall use the law of sines. But before we solve that, we need to understand that for SSA cases, there are possibilities that you could have one oblique triangle, two oblique triangles, or zero oblique triangle. And it would cost us amount of time if we are going to immediately solve it without considering the possible total number of oblique triangles that can be formed using these given values. So in order for us to identify that, we can actually have different specifications depending on first your angle measurement. Since angle A is acute, in this case there are many possible scenarios because if it is obtuse, there can only be two scenarios. That is either there is one oblique triangle or there is none. After identifying that A is acute, we will need to look at the relationship of A and B. If A is greater than B, automatically we have one oblique triangle. But for these given values, we can notice that A is less than B. For this situation, there are now three possible situations. There can be two, there can be one, or there can be none. In order to determine the final number of oblique triangles that can be formed using the given values, we need to look closely at the relationship of A and B sine A. This expression is the entire height of the oblique triangle. And if this is longer than A, there can be zero oblique triangle. If this is equal to A, there's only one triangle formed and it's also not an oblique, it's a right. Therefore, we cannot proceed with our solution. But if this is less than A, it would mean there are two oblique triangles. Let's try to solve this one. So B is 10. You have sine 23 degrees. Using this calculator, 10 sine 23 degrees is equal to 3.907, so on and so forth, or approximately 3.91. Now A is given as 7, and with this 7 is greater than the approximate value of 3.91. In this case, we are now sure that A is greater than your height. We have two oblique triangles. And with this, we will have two separate processes we call cases for the solutions of the remaining measurements of this triangle using the same original given 3. So there could be two measurement of angle B, two measurement of angle C, and two measurements for side C. Let's start with case 1. Case 1. Case 1 is where our triangle that can be formed will look like this. Let me increase the size again. Okay. Let's have it like this, and the other one will look like this here. So this is the first case where our angle is A placed here. This is your 23 degrees. The opposite side A is 7, and let us have this as your B equal to 10. Okay, this is case 1. Case 2 is what will happen if we are going to let me copy the same case here, lay somewhere here, and instead of case 1, this is our case 2. The second case is if this side A is moved here, or just like that. Okay, let me erase this angle here first, and like it. Okay, anyway, that's what will happen. In short, the new angle, okay, without this here, this triangle rather, the new triangle is this here, having the same measurement of 7. This one here, this side here, and that side. If we're going to complete the notations, this angle opposite side B is angle B. This is your side C. Angle C. This is your side C. This is the opposite now. That's your angle B. This is your angle C. And this is your side C. Look at what happened to the measurements for B. This is acute. This is now obtuse. So there are two different measurements for angle B. Angle C becomes smaller from this to simply this region here. And your side C becomes shorter for case 2. This is why there are two possible situations. So let's start with case 1. Again, we can use here the law of sine. So case 1, you have sine A 23 degrees over your A, which is 7. Let's pair it first in solving B over 10. So we're solving for angle B first. Cross multiplication, 10 sine 23 degrees is equal to 7 sine of B. Then we could divide both sides by 7 to cancel that out. Divide here 7 as well. So sine B can be solved as this entire expression, 10 sine 23 degrees over 7. But since we're solving for the measurement of angle B, we are going to use sine inverse. So 10 sine of 23 degrees all over 7. Let's input this in your calculator. So you have this. This was the numerator earlier. Let's try to input this again. Parenthesis 10 sine 23 to be divided by 7. Push equal sign to get the result. And you are going to have this notation of your answer equals. That's 33.93. Approximately, measurement of angle B is approximately 33.93 degrees. This is one measurement of the angle B. So since it's under case 1, let us label here B1. Now, before I will solve the measurement of angle C and side C here, let's just try to compare what is the measurement of the angle B to this situation here. We will not be using law of sines in solving for the measurement of angle B here because we might end up with the same result. Rather, we are going to use these concepts. This case 2 was made possible by placing or translating this side to this region here. But that's the original, same with the original equation. In short, this angle B here earlier is 30.93. That's also the angle here. So this also measures 33.93 degrees. Approximately 33.93 degrees. I would like you to focus your attention to this triangle here, the residue of your case 2 after taking from your case 1. This triangle here, the red one, is an isosceles triangle because this measurement is 7, which is also the same as this measurement. Much can we say about isosceles triangle is related to the measurement of the base angles here. For an isosceles triangle, the base angles are equal or congruent or have equal measurement. This means this side here, or rather angle, also measures 33.93 degrees. What is this information all about, or what's the purpose of this information? Notice that we are solving this angle B here, not 23 because 23 is the angle A. This measurement here. And the relationship of this angle and the blue colored angle is that they are forming a linear pair. And according to the linear pair postulate, they are supplementary. In short, the sum of these two angles is 180 degrees. Without using the law of sines here, we can solve for the measurement of angle B as, again, this is your angle B, the blue colored angle, being supplement to 30.93 here, which is again the base angle for this, which was originally solved here as measurement of angle B1. So this is equal to supplementary, meaning they sum up to 180 degrees. Don't be confused, this 180 degrees is not the triangle angle sum theorem, but the concept of linearity or linear pair. So less 33.93 degrees. So since it is approximated value we used a while ago, the measurement of angle B for case 2, let's label as B2, is approximately equal to, let's try to subtract that, 180 minus 33.93. You have 146.07. Again, 146.07 degrees. Compare the two measurements of angle B. You have here 33.93, 146.07. They are same angle B notation, but of different origins for case 1 and case 2. This is acute. Yes, it's acute. This is obtuse. This is obtuse. That's the difference between case 1 and case 2 because we have two oblique triangles here as shown earlier. Now that we are done with this, let's proceed to the measurement of angle C and side C later. So let's increase it again here. I'm going to increase it a little bit further. Okay. So the measurement of angle C here and even the angle C on this case 2 we'll simply use the triangle angle sum theorem because we already have the measurement for angle A and the solved different values for B. So for the measurement of angle C1 for case 1 is the difference of 180 degrees and the original 23 degrees, and this B1 33.93 degrees. For the measurement of angle C2, same concern, 180 degrees less same angle A, 23 degrees less angle B2, which is 146.07 degrees. So let's try to solve them independently. So for C1, that's 180 degrees minus 23 minus 33.93. That's approximately 123.07 because this is approximation. So the measurement of angle C2 is approximately 123.07 degrees. For the second angle, for our C, this is approximately still because your B2 is approximated value. So you have 180 degrees less 23 less 146.07. So you have approximately 10.93 degrees. Now we will be using these two separate measurement of angle C to solve for the side C, pairing it with the same pair as earlier for angle A. So you have sine 23 degrees, sorry, that's 3 degrees over 7, that's for your pair here, must be equal to the sine of your angle C, 123.07 degrees over C. That's different here because even if you're using the same pair of angle A and side A, your measurement of angle C is 10.93 degrees instead of 123.07 C. So let's solve them independently. Let me not label it C1 or C2 in the meantime because I would like everyone to follow the process. So C sine 23 degrees is equal to 7 sine 123.07 degrees. Divide this by sine 23 degrees to cancel that out. You will have here sine 23 degrees. So C is approximately the entire value of this expression. Let's put the correct parenthesis, 7, sorry, again, parenthesis 7, sine 123.07, close, divided by sine 23 degrees. That's 15.01 units. Approximately 15.01 units. For this region here, it's still C sine 23 degrees, but it's equal now to a different measurement. 7 sine 10.93 degrees. Divide both sides by sine 23 degrees to cancel that out. You have sine, sorry, that's sine 23 degrees. So this was C1 earlier, so C2 is approximately this. So let's see this again. Parenthesis 7 sine 10 point, again, parenthesis 7 sine 10.93, close it, divide by sine 23. So you have 3 point, round it up to two decimal places, 40. So 3.40 units. So notice the difference of the side measurement of C, which is also true with the other variables. Now this was case 1 versus case 2, but both of the cases still follow the same concept that the side opposite the largest angle be your longest side. For case 1, your largest angle 23, 33, this is your largest angle. So C is 15.01 versus 10 versus 7, that's your longest side. Your smallest angle is 23 degrees, so 7 is your shortest side versus B, which is 10, and versus 15, which is also true with this case here, case 2. Our largest angle is angle B, that's 146.07. Our side B is 10 versus 7. Our C is 3.4, very small. That's correct. And our smallest angle is actually 10.93 degrees. That's C2 here. So side C should be shorter. 3.4 versus 7 versus 10. So this is the very lengthy process when you have two oblique triangles for SSA situations, but still using law of sines and the appropriate relationships that you can draw in any oblique triangle.